Well, hello everyone, and let's try to resume the foundation engineering class. We are still on the chapter 6, design of mat foundation. So last time we talked about combined footing, different type of combined footings. And this time we are going to talk about this point number 3 and point number 4, the common type of mat foundation and the bearing capacity of foundation. I think the point number 4 is very interesting. Okay, so let's go and start with the first one. The first point of this lesson, which is the third one of this chapter. Common type of mat foundation. What are the different type of mat foundation? So already I hope you know what is mat foundation. We defined that previously. We gave several definitions. So this is mat foundation. It means the whole building will be resting on this foundation, one single foundation. Okay. So this foundation is a large combined footing that, as I said, it covers the entire building footprint. Okay, and it supports multiple columns coming. So you can count them if you want. Okay, so it is used mainly when the bearing capacity of the soil is very low. So uh, we sometimes prefer to go for mat foundation instead of using single foundation. Individual foundation, if it has to be used, it will take maybe more than half of the building area. So it's not economic. So for economical reason, the economical purpose, we go for the mat foundation. Okay. So what are different type of foundation? We will show them here. This figure is showing A, B, C, D, and F. You can see for each case we have plan view and a section. Okay. So if you take the first one, this one, A type, you can see that this is a uniform. Uh, let's say the thickness is uniform of the mat foundation. You can see, and you can see the columns coming on the foundation. If we take the B, okay, this one, the A1, the name is flat plate, okay, and the second one we have flat plate thickened. So it means we have this kind of a bit crampon columns coming down. Okay, and we have number C, the case C, beam and slab. Okay, that means it like when you are doing roofing, or let's say the top of the building, not roofing, you have beams and slab included. So that's number the C, the case number C. Okay, and the beams run both way, and the column are located at the intersection, both ways, this way and this way, and we have the column at the intersection of beams, and we have the case D. It is kind of similar to this one, okay, but we have this kind of uh, pedestal on it, And we have the last one, which is a slab with basement wall. Okay, you can see basement walls, something like that. So there are several types, but we will take one way, uh, all of them. The design is similar, how to design the bearing capacity, okay? So we can also use pile to support the mat foundation in in order to reduce the settlement. If you have a high compressible soil, you can do that, okay? And if you have high water level table, using pile also can help to control buoyancy. And we can see here, this figure is showing a comparison between embedment and width of single footing and mat foundation. You can see here DF for the single footing, for example, it is this distance. But for the mat foundation, it is from here to here. And for the width, of course, this dimension and this one, that one is easier. So this is example of flat plate mat foundation being under construction here. This is just a photo, okay? Let's go for the next point, which is the maybe most interesting point. How to estimate the bearing capacity of mat foundation, okay? So remember the bearing capacity of shallow foundation. We did it, I think, chapter 3 and chapter 4 also, even chapter 5. Chapter 3, 4, and 5. 3 was the general bearing capacity. Chapter 4 was special cases. Yeah. And chapter 5 was settlement. So the gross gross ultimate bearing capacity of mat foundation also can be calculated from the bearing capacity equation of shallow foundation like this equation. So if you don't remember this, I recommend you go and revise chapter number 3 we did. This formula was included, and you remember the bearing capacity factors and and let's say shape factor, depth factor, and inclination factor. All these in chapter 3. Okay, all of them. So if we consider now in case of mat foundation, what will be B? Remember, B was in shallow foundation. B was the width of the foundation. In this case, B will be the smallest dimension of your foundation. Okay, and if you want the net bearing capacity, remember you have to remove the Q, the overburden pressure. Okay, this Q, which is just dF multiplied by gamma. It's easy. Okay, so this is the net. This is gross. This is net. Net means, because if you, this is including the place where the foundation itself will take, but you have to remove that part of soil, right? So that's why you have to take this out. This is the net bearing capacity. So this now net allowable bearing capacity, because this is net, but you, of course, you cannot load at 100% your soil. You have to leave some margin safety. Okay, that's why you have to divide this net bearing capacity by a certain safety coefficient, to get what we call net allowable bearing capacity. Okay, so the factor of safety, sometimes 3 for clay. We have sometimes this value, but not always. For sand, we have 3, but for sand, I mean mud foundation in sand is mainly controlled by the settlement. They're not really by the bearing capacity, and we will talk about this, okay, in the following slide. Let's consider the case of clay, saturated clay. If we talk about clay, it means the NC. Please go back and see the chapter number 3 again. The bearing capacity factor contribution of cohesion is 5.14. NQ is 1 and N0 is 0. Okay, that's for clay. Means phi is 0. There is no sand. And if we consider that vertical loading is applied, what does it mean exactly? It means the inclination factor FCI, FQI, F gamma I, they will not be, they will be just 1, 1, 1. Okay, there is no inclination. The load is not inclined. Vertical loading. Yeah. So in that case, what we will need will be maybe shape factors and depth factor. But so this is what we will have in that case. Okay. But for saturated clay, for clay, remember, for clay, all this will go away. We will not need this part. Okay. We will not need this one. It will be 0 because n gamma is 0. It is here. It's written here. N0, n gamma is 0. So all this will go away. Okay. And this one, all these are 1, 1, 1. So it will remain only Q. Okay. Then here, remember that the load is not inclined. So this one is 1. So if you check very well, we just replace the C prime cohesion by the undrained cohesion because it is saturated clay. Okay, Cu. Okay, then you will see that we have exactly same equation here. So this one is coming from here. Okay, undrained cohesion.